Welcome to lecture 10, which is about the accuracy control using GNSS and GCP while doing drone surveying. So in this lecture, you will learn how to select and establish ground control points, because these are very important requirement in the drone survey. What is the role of these GCPs in survey, and how we control the accuracy using GCPs, and how we can control the accuracy using the GNSS data. So drone data accuracy is the degree to which the data is captured by a drone. So it reflects its true measurement and spatial relationship in the surveyed area. There are several factors which will include the accuracy of the data which we are collecting from the drone system, whether it is a LiDAR based sensor or it is a photogrammetric sensor. Flight planning could be one. The precision of the GPS or GNSS device which we are using. Camera calibration in case of the photogrammetric, and post processing techniques, the kind of technique or the software which we are using to process the data. So these are some of the factors on which the accuracy will depend. When we are doing drone survey alone, we will get approximately 2 to 5 meter accuracy. That means our point, the object on the ground, can be 2 to 5, can have 2 to 5 meter error, which is not sufficient for engineering and land surveying. It could be sufficient when we are doing visual mapping, but for topographical mapping or construction monitoring of the area, infrastructure planning or urban planning, what we require is the better accuracy. We require centimeter level accuracy. So for example, a road alignment survey or a property boundary survey does not exceed even 1 meter error. You should not have more than a meter error, otherwise it will change its real world coordinate. So we need to collect very accurate and precise data from the system. Now whether we are using photogrammetric drone, as you can see in this particular diagram on my left, or whether we are using the LiDAR based drone systems, accuracy of the data is required in both the systems. In the photogrammetric based system, we are taking the images and there is some overlap in the images, and we are creating the 3D model in the overlap region. LiDAR data will give us the point cloud data of the area. It is already in the third dimension, so we can get 3D model from this data directly. But both have to be accurate. When we are talking of the LiDAR drones, as we know that these drones will carry a LiDAR sensor which will collect the data that can be used for very detailed 3D models. We create 3D models for several applications and industrial applications. And this LiDAR sensor can help provide us most accurate and high resolution 3D models which are available. And particularly when we are working in the forested region, the advantages of the LiDAR sensor increase. These LiDAR drone, it is different in approach with the photogrammetric drone, because here it will take hundreds and even thousands of photographs in photogrammetric drone, and we have to stitch them together. We have to create a mosaic from all these photographs. So this has to be very accurate process. LiDAR beams will penetrate through the foliage, through the forested area, whereas the photogrammetric system cannot make. So LiDAR system is a very powerful tool when we are discovering the new sites, like in archaeology, or we are discovering what is on the ground below the tree. So all that information we can get from the LiDAR, where photogrammetric systems cannot provide us that accurate. So if we see LiDAR and photogrammetric drone, regardless of the details and the accuracy, both these systems, LiDAR based and photogrammetric based system, will provide us good results, excellent results for 3D modeling. But out of the two, the LiDAR is considered to be most accurate method surveying solution than photogrammetric solution. LiDAR will provide highly accurate 3D measurements of the environment, and the accuracy of the LiDAR can be as high as few centimeter. So, this is a great advantage of using the LiDAR sensor. Now, depending upon the sensor and depending upon the software which we are using to process the data, we however get the accuracy. Photogrammetric drones may not capture the data so accurately, particularly in low contrast environment such as snowy terrain or featureless landscape. But LiDAR provides very accurate measurements that can be used to improve the accuracy of the photogrammetric data. So, if we are using both the data products together, then maybe we can use some of the LiDAR data to improve the accuracy of the photogrammetric data. LiDAR can capture data about the environments that may not be visible in the photograph, such as the bridge underside or the bridge interior, that we can collect with the help of the LiDAR. So, each system, as far as the accuracy of the data, as far as the quantum of the data is concerned, they provide us different forms. Now, combining this LiDAR and photogrammetry data for improved information and improved accuracy. So, when we are combining this data, we get the complete picture of the environment, and this can be helpful in various applications, whether it is for construction industry or environmental monitoring or conservation activity. As we know that this LiDAR data can generate very accurate measurements of the tree height and density, whereas photogrammetric data can provide us a detailed 3D model of the forest canopy. So, if we can combine these two data, we have the forest canopy data in the form of the photographs, and we have the data in terms of the tree height and the density. We can have a complete understanding of the forest ecosystem, including the distribution of species in the area, the impact of the environmental factors such as the climate change and forest management practices. So, when we are combining these two data, there are several new applications where we can get very high precision of the data. So, how we can actually improve the accuracy in photogrammetric drones when we are taking the photographs of the area? So, there are some ways, some precautions which are to be taken to improve the accuracy. The first thing here is the ground control point, we call GCPs. So, we incorporate GCPs in our surveyed area. These are the points whose coordinates are known to us, 3-dimensional coordinate x, y, z and known to us, and they will be used to improve the accuracy of the photogrammetric output. So, with the help of the ground control points, actually we will analyze the photogrammetric data. We collect accurate GPS coordinate of these points. How the coordinates will be known? That we will collect very accurate GPS coordinate of these points and include them in image capture. So, we will have them in the area well distributed so that they are captured in the subsequent images and we can use these points. We have to take care of the overlap and the sidelap also. We have to ensure there is sufficient overlap, 70 to 80% forward overlap and 30 to 40% is the side overlap between the consecutive images. And this overlap, sufficient overlap, will ensure proper coverage, and also when we are matching the images, when we are creating the mosaic, as well as creating a 3D model from these images. Then continuation of the slide, then consistent flight altitude is important. We have to maintain a very consistent flight altitude throughout the survey to ensure we have the consistent ground resolution and scale of the mapping. So, we use appropriate flight planning software or tools to do that, so that the drone is maintaining the altitude accurately and stability. Check weather condition. Choose suitable weather condition for the drone flights. When you are flying to the area, you have to avoid strong winds or heavy rains or poor visibility conditions, as they can impact the stability of the drone as well as the images which are captured from the photogrammetric drone. So, good weather condition is essential. Quality control. You have to perform quality checks on the photogrammetric output. We have to validate the accuracy of the generated point cloud data or the 3D model by comparing it with the ground control points or the reference data. So, there is some reference data which we have not used actually to create 3D model, we will keep them for quality check. So, this step will actually rectify if there is any other error or improve the accuracy of the model. Now, this slide shows how accurate is my photogrammetric drone data. It depends upon the ground control points, number of ground control points and their distribution. It will also depend upon the terrain profile, that means the undulations in the area from high altitude to low altitude, elevations which are present in the area, image overlap, how much overlap we are taking between the subsequent images and the weather condition. What are the weather condition when the photographs have been taken? So, this gives a comparison of the the ground survey with the drone survey. So, this shows a comparison and it says that we can save lot of time. If we see at the end, total time taken as 2 to 3 weeks when we are doing ground survey of an area, and the same area we can actually complete when we are doing the drone survey 1 to 4 days time, depending upon the objective and depending upon the other parameters. But this gives a broader view that how much time we can actually save when we are doing ground survey as well as we are doing the survey from the drone. Little bit about the LiDAR based drone. So, a LiDAR sensor which we are attaching to a, for example, a fixed wing drone can cover 4 square miles in one flight, very large area in one single flight with an absolute accuracy of 10 centimeter, which is a very good accuracy in the horizontal direction and 5 centimeter in the vertical direction. Planimetry accuracy and the height accuracy, we are getting 10 centimeter and 5 centimeter respectively. And this is some of the highest fidelity data currently achievable by any aerial surveying method. So, this is considered to be the best method of collecting the data with very high accuracy. Now, there are various combination of the LiDAR sensor and the drone models which will actually yield different types of results. So, it will also depend upon the type of the model which we are using and also the sensor which we are employing, the accuracy will depend upon that also. Now, we talk about the ground control points. So, these are large photo identifiable targets. Actually, those targets which you are selecting on the ground as ground control point, they should be identifiable on the photograph when you are taking. So, you are placing on the ground within the boundary of the drone survey, the area which you like to complete. Now, these points, they marked with the highly visible targets and they are geo-referenced using GPS or GNSS data. So, we know the coordinates of these points and we are using the coordinate to align the drone images with the real world coordinates. So, we will align geo-referenced, for example, the drone images with respect to the known ground control points. GCPs can also be used in addition to drone survey. Those GCPs can also be used for engineering design, construction progress and monitoring and precise mapping application in that particular area. A low cost drone without GCPs may give error of about 5 meter. So, the GCPs are must because you get very large error without GCPs. 5 meter horizontally in planimetry and 20 meter vertically from its true location. So, this is we are talking of the low cost drone without using the GCPs. The low absolute accuracy will limit the use for engineering design or track changes through cut and fill analysis if we have to do that kind of way. So, we need to collect the data with a greater accuracy, higher accuracy. The drones which fly much lower altitude than aircraft or satellites, and data is collected also very high quality because the altitude is much lower. So, we can get nowadays centimeter level accuracy data, which is very good for carrying out a very large scale mapping for infrastructure planning. Now, to ensure the absolute accuracy, ground control points are known coordinates which are used. So, there is a term called absolute accuracy and there is a term called the relative accuracy. So, we are talking here the absolute accuracy of the point. These GCPs are used along with the drone and GPS data in post processing. So, when we are post processing the data, these GCPs are playing very important role, and the data collected can be georeferenced with geographical coordinates collected by in-house GPS. So, we have to maybe carry out a separate survey in order to know the coordinates of these GCPs using a GPS survey. There are several advantages of using these GCPs in our drone survey approach. Enhanced survey precision is one. We can achieve centimeter level accuracy because the GCPs will improve our positional accuracy very significantly as compared to the standard drone GPS data. We are also getting reliable elevation data. So, planimetric data as well as the elevation data is also very reliable because when we are doing topographical mapping or construction site or we are developing the contours for that particular area, determining the slope, then the elevation data has to be reliable. Improved 3D modeling and digital elevation model is another. We can create a better terrain representation. So, GCPs will enhance the quality of the elevation data and we can have more and more accurate DEMs to create slope, aspect and other parameters. Refining the structure model for industry like construction industry or mining industry, these GCPs will ensure very detailed 3D representation of the infrastructure in the area. These GCPs also in drone photogrammetry and in LiDAR mapping both, they will help us to correct any distortion which is present especially and ensure that the maps which are generated, they are accurately positioned with respect to the ground orientation. These GCPs are placed strategically throughout an area to be mapped. So, we have to select very strategic location of these points and their known coordinates will be used to calibrate the drone captured data. So, raw data which is available from the drone, we will actually apply the corrections with the help of these GCPs to calibrate that data. How GCPs can improve geospatial accuracy? They will correct the georeferencing error. So, drone images will have some distortion. Maybe when we have photogrammetric images, due to the camera angle, due to the elevation of the terrain, relief is present. So, we will have lens distortion. So, there could be some distortion which is present in the data. These GCP will help us to adjust for those error in the data. They will provide fixed coordinates. So, unlike drone GPS which may have a slight inaccuracies, these GCPs will offer very high reliable real world ground coordinates to refine our aerial survey results, the raw data which we are getting. What is the size and what is the shape of the GCPs? Now, the literature says the standard size of this is like a square of about 60 centimeter by 60 centimeter, that is the about 2 feet by 2 feet. The shape and size should be easily detectable when you are taking the data from a certain altitude. So, when you are creating the GCP's mark on the images before processing the flight, you have to ensure that this is visible on your image. The ultra high resolution cameras or low altitude flights The smaller GCPs may be acceptable if you are using ultra high resolution camera or your flight altitude is very low, then you may have a smaller GCPs than 60 centimeter by 60 centimeter. But you require larger GCPs. Bigger GCPs are typically required for manned flights. Now these GCPs, they are available in various shapes, size and color. Ready made they are available, and we can make a selection from those also. So black and white GCPs, but out of the one which are colored, black and white works very reliable. That is what the literature says and has been used as a standard for a very long time. Because the colored one sometimes merge with the background also. The ideal color will depend although on the background terrain colors. So the selection of the color of the GCPs will also depend upon the terrain background. Reusable black and white checker point painted X cross on the ground typically appears very well on the drone images. So it has been found that the X sign, the cross sign, which is black and white checker, if they are kept on the ground, they are clearly visible on the drone photogrammetric images. We have to avoid certain points selecting at the GCPs like tree or shadow or a vehicle parked or some temporary surface. So we should avoid selecting those as GCPs. Instead, we should select naturally photo identifiable targets on the ground such as traffic arrows, manholes, etc., a corner of the building that we can select as the GCPs. We always take a ground picture of the object which we are selecting as a GCP to distinguish it easily later while we are processing the drone data. So we can take help of those ground picture which we have taken about those GCPs. Now this is the picture which shows that the GCPs, they are available in different size and different color combination and different shapes. How many GCPs and where to place GCP? That is another question in the mind. Technically, many drone mapping software can work with as little as 3 GCPs, but the best practice is to use a minimum of 5 GCPs for the flight area, so that you can control the entire area, maybe the 4 at the corner and 1 in the middle. So minimum of 5 GCPs are recommended, but you will find that the literature, the 3 GCPs have also been used, but you do not find very good accuracy from them. They should be spread evenly across the survey area. So they should not be confined to one region only. As I told you, 4 corners and 1 in the middle is like a spreading or covering the whole region. You have to include high and low elevation if the terrain varies. If there is a height variation, great height variation, then you have to select some points on the higher elevation and some points on the lower elevation side. The effectiveness of an area is inversely proportional to the distance from the GCPs. You will find at the end the areas which are closer to the GCPs are very accurately mapped, and the areas which were away from the GCPs still have the distortion in the data. You have to draw an imaginary circle of 200-meter radius around the GCP, that is what the literature say, and the areas outside that circle will have the lower accuracy. Within the 200-meter radius area will have very high accuracy. So 200-meter radius is for low end drones such as DJI mini series, but this circle may be a larger circle in diameter for better cameras like DJI Phantom or 4 or so others, good camera. So this picture actually shows the distribution of the GCPs in the area. So you can see that the entire area is covered, well distributed and taken care of the low altitude and the high altitude areas. Examples of the bad GCPs: don't place them too close together because you really don't achieve anything out of it. Then don't use something that has any height to it. So don't keep the GCP on a higher object. Don't place the GCPs on the side slope because slope may not be stable slope. Don't push the GCP in an area where these may be disturbed by the change in the topography. How to obtain the high accuracy? Obtaining high accuracy survey grade coordinates for the GCPs is considered to be crucial, and most of the time this is done with survey grade RTK method, RTK GPS approach we will discuss later. So, when we are using GPS or GNSS sensor, a drone with a GPS receiver can receive signal from multiple GNSS satellites, and drone location can be determined by triangulating the relative position from the different satellites which have been captured. The precision and the location of that point will be determined by the strength of the signal which we are receiving from the various satellites, and the number of satellites which we are tracking within the range will determine the precision of the point. So, GPS, a global positioning system, is a specific system which is developed by the USA, while GNSS, Global Navigation and Satellite System, is a general term, umbrella term for all satellite navigation system, as I told you before also. The GNSS will help the drone to determine the location where it is on the earth, and GNSS is considered to be more advanced than GPS, as it is using multiple satellite network to improve the accuracy. More the number of satellite, more accurate the position is determined with the GNSS. There are situations where drone will lose its connection while it is moving with the remote control, or maybe the battery level is low. So, there the GNSS technology will help us to automatically navigate back to the takeoff position. This is called return to home, and thus it will ensure a very safe return to the challenging situation. Also, it will protect the costly drone equipment from being damaged. GNSS technology will also help us to create virtual boundary geo-fencing to restrict the drone to enter into these sensitive zones. So, without GNSS on the drone, now without receiving the signals on the drone, sometimes onboard sensors like IMU, as I explained you before, it will gather the information on altitude, attitude and location, and it will allow the drone to hover and maneuver. Additionally, the LiDAR sensor will enhance the drone navigation capability through the SLAM software, which I have explained you before. What are the limitations of using the GNSS on drone? Drone typically will use a consumer grade GPS module, which are generally less accurate as compared to the high precision system which are used in the surveying equipment. So, accuracy of the data is affected by the number of satellite a drone can track at a given time, as signal from the fewer satellites can lead to the low precision of the coordinates. Now, dense and taller objects, if they are present, like buildings are there, tall building, indoor objects, or even the strong winds can interfere with the GPS signal and will affect the accuracy. The other limitation could be that the initial investment when you are having a complete system is very high, and this will reduce the use of this. When you are acquiring RTK, PPK, the entire system, the cost may go high, initial investment is high. There are some major sources of GPS positional error, and we have to take care, apply those corrections so that we do not get the much error in the data. So, it could be atmospheric interference, it could be the ephemeral orbital path data error, and the multipath effects. These are the major sources of errors which could be present in my GPS data. Then satellite position will also affect the accuracy of the GNS. So, GPS receiver will use the triangulation method to calculate the position of the GPS receiver. So, if the satellite's position is not favorable position, then maybe we will get the error in the position. If we have the installation mistakes when we are starting our work, or GNSS receiver quality and features, they are not good, we get error. We also get the error from the interference with the surrounding environment also. GPS which we are using in the drone survey is a standard GPS, which is a GNSS system, which is utilizing the satellite signal to correct the position, but within a few meters only. So this is good for general mapping, but lacks precision which is required for the professional surveying competition. So what we are doing is we are using a method called RTK method, which is a real-time kinematic GPS method, and here we are using a base station, a known station whose coordinates are known to correct for errors. Here we can get the centimeter level accuracy, very good, ideal for construction site mapping, precision agriculture and cadastral survey. And the third approach is the post-processed kinematic GPS, which is called PPK, and what it will do, it will capture the GPS data during the flight and apply the correction afterwards using the capabilities of the software. So it provides greater accuracy than RTK in areas where there is a loss in the signal, where there are not proper signal, and it is making it useful for forestry, mining and large scale land mapping. So we will discuss more about the RTK and PPK approach. So RTK will use carrier face measurements, wavelength approximately 20 centimeter. We require two GNSS receiver. One receiver is placed at the base station, which is known as the known point. Another receiver is Rover, which will be installed on the drone systems. The base station will actually send the corrections in real time to the Rover system via internet protocols. So the rover will apply these correction and we can get 1 to 3 centimeter accuracy. So very high accuracy we can achieve with the RTK method. This particular slide will show you that we have a base station here which coordinates are known to us, and rover is fixed in the drone system which is over here, and the base station will continuously send the corrections to the rover station and we can get very high accurate data. So this is the RTK field workflow. We will set up the instrument at base station, we will establish the communication between the two, we will connect the rover to the base system and we will fly the drone, collect the data, then we will fix the quality of the monitored data, and this advantage is we get the instant result, the corrections are applied immediately. We require fewer GCPs, ground control points, but it has the limitation also. Limitation is that it will require very stable communication throughout the data collection method, and baselining under 10 kilometer only this method is very useful. So this RTK will improve the accuracy, and this slide shows that how we can actually improve the accuracy by setting up the ground control station. We apply the real time differential corrections to our measurements, drone communication and correction applications apply, and we get the enhanced accuracy on the fly mode. So that is how the RTK will improve the accuracy to the centimeter level. But there is another technique which is called PPK technique, and PPK technique basically is the post process kinematic technique, and the concept is same principle as RTK, but no live collection is required here. We will collect the data, and after collecting the data we will process the data through a software like IMLID Studio or RTK Lib, the software which can be used for processing this data. It has advantage, you do not have to make a live link between the base station and the rover station. It works well in the remote or the forested area also, and you get as high accuracy as in the previous method, 1 to 3 centimeter. So nowadays post processing kinematic method is also preferred. So this slide shows that what is the steps involved when we are doing field setup. We will deploy the base receiver, known station whose coordinates are known to us. Drone will log the data, and after flight we will download the data and will process the data. The advantage of this is reliability, accurate, no live collection needed, no risk of communication lost, enable the longer baseline up to 100 kilometer. It works very. This is better consistency provide along the long missions. but it has a limitation, like while you are processing the data, it will take long time after your flight is over to process the data. So this diagram shows the post processing technique. Again, the base station and the data is being collected by the drone, and the data is processed later on by the software. Now the question comes, how accurate is my GPS data on a drone? The performance is directly linked to how well it has been calibrated and what correction data is available. Basic GPS accuracy will provide within a few meter, but however, when you are pairing it with RTK or PPK correction, the accuracy you can improve to the centimeter level, and applications could be cadastral survey or the smart city development. So accuracy of the GPS on a drone can vary. It depends upon several factors, but it is typically in the range of 1 meter to 5 meter horizontally planimetry, and plus minus 3 meter to 10 meter vertically if we are not using any RTK or PPK method. We apply some accuracy check also. These are the standard method where we find out root mean square error. We know the coordinate, we compute the coordinate, we find out the error of those points. So we can actually, through root mean square error relationship, we can find out the accuracy of the data which you have processed. Then this is a comparison between the RTK method and PPK method. As far as the accuracy is concerned, if you see the second column, it shows that you can improve the accuracy from meter to the centimeter level when you are shifting from the standalone GNSS to RT or PPK approach. You can improve the accuracy of the collected data by using RTK or PPK system. You are deploying the GCPs for reference, having very high resolution sensor, or the cameras have perfect flight planning. So this requires certain exercise. Before that, you have to ensure the weather condition, good weather condition, and open flight area, so that you are not losing the signal. You have to choose the system that is best suiting to your project and requirements. You have to optimize the flight planning by setting adequate overlap between the images and flying at a suitable altitude. So how to fix a weak GPS signal on the drone? You have to ensure optimal GPS signal reception. You have to ensure that the drone is in the open, unobstructed outdoor area when you are collecting the data. You have to maintain a clear drone surface. Sometimes there are some stickers which are sticked on the drone system, so you have to avoid that kind of things. So this slide shows comparison of the various drone accuracies when you are collecting the data from different kind of drones, that what is the accuracy level which you can achieve from the different models of the drones which are available. Then calibration of the sensor is also very important. The literature says that over a time period the error may accumulate in the sensor, so you have to actually correct for those errors. So calibration of certain sensor is required. So before flying a drone, it is necessary to calibrate the sum of the sensor. The advanced calibration techniques, however, they are performed in a laboratory which has manufactured the sensors. So factors that might affect the accuracy, there are many factors, but it could be loss of GPS, loss of altitude, loss of communication, too much wind, a pilot error, or fly away, automated system error. So these are some of the factors which will affect the accuracy of the data. Summary: the drone survey accuracy will depend upon the several factors which we have learned: GPS correction, image overlap, quality of the sensor, ground control point, their distribution and number, flight altitude, weather condition, data processing software which we are using. So we can actually get from RTK and PPK 1 to 3 centimeter accuracy, while the error range may be 1 to 3 times more when we are with the ground sampling distance. The future of the drones in accurate surveying actually is very promising. The drones are expected to have more and more multi-sensor systems with improved cameras that can capture very detailed topography, structural information, as well as handle very challenging terrains. So user can utilize the accurate drone data for large scale land mapping. So these are some of the suggested readings further. Thank you very much.